Hi, this is Mr. Spone here, and in this slide we're going to ask the question of why is it easier to boil water on a mountain. We're going to look at temperature during phase changes, and we're really going to look at the polarity of water in general, the nature of a water molecule. Why can you fit so many drops of water on a penny, and so on. What is surface tension, etc. We're going to start with water boiling. When we heat up a pot of water, the water is going to boil, evaporate, and enter the air as a gas. Actual particles of water leave the liquid and turn into a gas, and they, run off into the atmosphere environment. But as we know, when we study air pressure is real, and it's pushing down on us. When we look at our pressure mat in class or see many of the pressure demos we do, we know that air pressure is 14.7 pounds per inch squared. So air pressure is pushing down on the water, making it harder for the water molecules to leave. If there was a lot less air pressure, water would be able to boil and evaporate much easier. If you didn't see this, you will see this in the vacuum pump in class. We're going to take 80 degrees Celsius water from a tea kettle, and we're just going to suck some of the air out of it, and we're essentially going to show you water boiling at a temperature below the boiling point. So the boiling point of water depends on pressure. In order for water to boil and for it to evaporate, you have to overcome air pressure. So air is there acting sort of as a barrier, preventing water from changing phase. If we remove or decrease that air pressure, the boiling point becomes a little bit quicker. That's why if NASA had an astronaut once and they created a vacuum, which means there's very, very little pressure, they removed as much air as they possibly could, and they were doing simulations for space so the astronaut could train, and something happened with his suit. There was a malfunction, so he was exposed to a vacuum for a very short time, and I think he made it like 10 to 15 seconds before he blacked out. And he said the one thing he remembered was right before he passed out, the saliva on his tongue was boiling, and it wasn't hot. It was just because there was so little pressure in the chamber that the water on his tongue was able to boil right away. So water can boil at temperatures well below 212 if we reduce the pressure. Because in order for water to boil, it has to overcome air pressure. If we remove the air pressure, boiling becomes much easier for water. So why is it easier to boil water on a mountain? Well, as you go up, there's less air, there's less pressure. The atmosphere is only so big. When you're on the surface of the earth, right here, there's a lot of air above you. A lot of air above you. When you're on top of a mountain, there's only a little bit of air above you. And of course, the air is going to be a little denser, closer to the earth due to gravity. So the idea is there's less air, less pressure as you go up. So theoretically and actually, if you were trying to boil water on a mountain, it would be a little bit easier than boiling water on the surface of the earth or at sea level. Because there's simply less air above you, there's less air pressure, there's less resistance to boiling by the atmosphere. So the air would actually allow you to boil water pretty quicker. And that's why mountain climbers use supplemental oxygen. The air is really thin as you go up. There's less of it, and they need, tanks to survive the higher they go. And another reason to look at, air pressure is one reason that impacts the boiling point of water. And that's why it's easier to boil it on top of a mountain, air pressure. But there's other considerations for just boiling in general. And we're going to talk about water molecules. Water molecules are attracted to themselves. A water molecule is made up of two hydrogen atoms chemically bonded to an oxygen atom. And it turns out that water is a polar molecule. And what we mean by this is water has a plus side and a minus sign. The hydrogen end of water is positively charged. The oxygen end is negatively charged. For reasons you will learn in chemistry, dealing with electronegativity. You can, if any of you rubbed a balloon on your head and stuck it to a wall, you could actually rub a balloon on your head and have it bend a very narrow stream of water. I show this in class. You've probably seen it if you're my student. So water does have a plus and a minus side. It is a polar molecule. Recall that if you had two magnets, if you had two bar magnets, if you had a north side and a south side near one another, they would attract one another. Opposite poles attract. If you had a north side and a north side of a magnet near one another, they would repel. Like poles repel or they repulse one another. Well, and again, in my room, I have these magnets. These must be like poles. They're repelling one another, so you can get magnets to almost seem like they are floating in midair, which is exactly what they look like. bar magnets and a pencil or anything like that. I have a bunch of these in my room. They're pretty cool to play with. But electrical charges are also like tiny little magnets. Opposite charges attract, and like charges repel. So if you had two negative particles next to one another, they would push away, they would repel. If you had two positives near one another, they would repel. If you had a negative and a positive near one another, they would attract together. So water has a negative and a positive side, and we know opposites attract. So water molecules are going to attract to one another. The oxygen end of one water molecule is going to be attracted by the hydrogens of another water molecule because opposite charges are attracting. Hydrogen bonds. And in order to break water molecules apart, these things are kind of like glued together. They're like pulling magnets apart. You have to pull them apart. They require energy to break. So this is another consideration for boiling. We have surface tension. And let's see what this means. Let's say this is the surface of a liquid. This is a water molecule right now. In order to boil, this water molecule has to leave. It has to overcome air pressure, but at the same time, this water molecule is being pulled this way by opposite charges. It's being pulled this way. It's being pulled this way, this way, this way. So it has to overcome something we call surface tension, the cohesion of water on the surface. All water molecules are generally going to be attracted to one another. And in order for this to boil, it has to overcome the fact that this water molecule is being pulled down by water underneath it. So that's another impact on boiling point. Objects that aren't as polar as water, that have lower surface tension, will boil more easily, like alcohol. When you do your drops on a penny lab, when you put soap in water, the penny holds far less water, so that means the surface tension is lower. Soapy water will boil at a slightly lower temperature than regular water. So that's surface tension. Surface tension also impacts boiling point as well. So in order for water to change not only from liquid to a gas, not only must you overcome air pressure, which is pushing down at it, but you have to overcome surface tension as well. And this does help a little bit explain different boiling points of different liquids and materials. And there's one other thing I want to look at in terms of water and its polarity. Just remember, water molecules like to click together, plus side, minus side. That's how we fit so many drops of water on a penny. You get a little bubble forming over the rim of the penny because all the water molecules are sticking together. When you have a phase change, temperature remains constant during phase changes. So here we have a phase change of water graph. And in this area right here, we have ice melting. And the temperature is staying the same. As we go from, say, 2.5 minutes to 12.5, the temperature is staying at 0 degrees. Temperature is constant. Why? Because the ice is melting. The energy is not being used to move the water molecules faster. Right now, the water molecules are locked together as in a crystalline lattice. They are locked together like this right here. The oxygens are connected to the hydrogens. They are locked together. In order for ice to melt, so the particles in the liquid can slide around one another, you have to use energy first to break these hydrogen bonds. And once you break the hydrogen bonds, once all the ice melts, then the water starts heating up. But until these bonds are broken, the energy is being used to break them, not to make the water molecules move faster or acquire greater temperature. So this graph right here is going to show liquid water. And as you're heating liquid water with fire, fuego, or just being in a big room that's much warmer than it, the temperature is going to rise with time. This is water getting warmer as you go up. And during a phase change, when ice is melting, temperature is staying the same. Why? Because the temperature is being used to break the hydrogen bonds, not to move the molecules. And once you get to the boiling point, again, temperature is going to level off. So at this point, we see that temperature stays at 100. And this is the Celsius scale. 0 is freezing, 100 is boiling. Why? Well, once it can't get any hotter. It gets hotter. It's evaporating and boiling away. But the idea here is you're giving the water enough energy to essentially break free. And at this point, what the water has to do is it has to overcome the surface tension and air pressure. And all this extra energy goes into doing that. There's a lot of stored energy in the water. It has to break away from the chemical bonds, because even not only just ice, but liquid water drops are also attracted to one another. So when you're boiling water, the molecules have to fully break apart into a gas and separate themselves, overcoming surface tension and air pressure. So The polarity of water is pretty important, explains a lot of things. There is surface tension at the top of water because water molecules being pulled down by the water underneath it to the left and to the right. So it's almost like there's a thin film at the top of water, which does allow certain things like water striders to walk on top of them, or allow you to, if you want to, get a paper clip to float on water, even though it's denser than water. And the important key here is water molecules. There's a plus side and a minus side. Water molecules stick together. They have cohesion. Water molecules are attracted to one another. This creates surface tension and a whole host of things due to the electrostatic force. Opposites are attracting, and so forth. Just like magnets, electrical charges, same thing. So hopefully you have a slightly better understanding of boiling point, the polarity of water, and phase changes. This is Mr. Zapone. I'm out.